Hi and welcome. It's now time for Physical Sciences on Saturday Extra. My name is Tinyiko Okosa. Now, today we're going to talk about something very special. It's a lesson based on the chemistry of carbon. And I think you can immediately begin to tell what are we going to talk about. We're going to be looking at organic chemistry. And to start with, we will be looking at the organic molecules. Right. Now, in the lesson, we will, like I explained earlier on, we'll be looking at this unique element called carbon and how it bonds with other elements, with other atoms. Okay? And we will focus a lot on molecules known as hydrocarbons. We will also be talking about the terminology that is used in the chemistry of carbon or within the whole family of the organic chemistry. And we will also talk about a system that is used in the naming of organic molecules. And lastly, we will then be talking about the physical properties of organic molecules. Physical properties, things that we can see, we can touch, we can feel. Okay, those are the physical, what we can see happening, all right, with these particular molecules when they react with each other or when we just view them and try to observe what is happening or how they behave. So that will be the physical properties. Okay, that will include things like what happens when we heat them, what happens when we cool them off, things like that. Right. Let's now look at the uniqueness of this carbon atom. Now, carbon has got the ability to form 4 bonds. Okay? Now, how does this ability come about? Now, let's go back to some grade 10 chemistry work. If you remember very well when you were doing electronic configuration in grade 10, this is what you did. Carbon is element number 6 on your periodic table. Now, what does that mean? It means that it has got 6 electrons in total. If this is my 1s orbital, this will be the 2s orbital, and that will be the 2p orbital. Now, the electrons here, we have got 6 of them for a carbon atom to be neutral. So it would be 2 down there, 2 there, for us to have, now we are at 4, so we need 6. So it means here I would have 1, 2. Now the question is, I only have here 2 spaces that are half filled. How am I going to get 4 bonds? Because bonds is about sharing of electrons. Okay, so we know this. I'm trying to revise some of the things that we have done already. Bonds are formed when electrons are shared. Okay, sharing of electrons. Now, what happens here with carbon is that when this atom is at an excited stage, one of these electrons here goes up or gains energy, and it goes to a higher energy state. What happens then when that occurred? You don't have you don't have 2 electrons anymore, but you now have 1 only. So you've got now how many spaces where sharing of electrons can happen? You've got 1, you've got 2, you've got 3, and you've got 4. And therefore, carbon has the ability to can form 4 bonds. So that is what happens here for carbon to be able to form those 4 bonds. And it's unique to carbon. This is something very unique to the element itself. And another issue about carbon is that it has got this ability, catenation ability. What is catenation? Catenation is the ability to form long chains. Okay? Long chains of molecules bonded to the carbon atom. So in other words, you've got a carbon atom bonded to another carbon atom, bonded to another carbon atom. In that way, it has got that ability, catenation, to form those long chains, okay? Apart from these long chains, this carbon atom also has an ability to form, in the formation of those chains, it can also form rings. In other words, you can have a situation where you've got carbon atoms forming rings like that, okay? So this is one situation where we can see a ring being formed. Here we can continue and continue to have carbon added and added and added. So that is the catenation, all right? The ability of carbon to form long chain molecules, to form ring molecules as well, right? Now, like I said, we're talking about molecules containing carbon. And specifically, those molecules that we'll be talking about most of the time will be those that will be containing hydrogen atoms as well. So because they will be containing hydrogen and carbon atoms, we call them hydrocarbons. So what are hydrocarbons? Like I've already indicated, these are organic molecules consisting of hydrogen and carbon atoms. Okay, bonded together, of course. Now, where do we find this type of molecules? We find this type of molecules in things like crude oil. Okay? We can also find these molecules in substances like, or things like waxes. We can find them occurring as natural gas as well. Okay, so these are the sources of organic molecules, the hydrocarbons that we're talking about. Right. Now let's look at some terminologies. That's the terminology that is involved in organic chemistry. We talk of things called, or a thing called functional group. What is a functional group? Okay? It is a special feature of an organic molecule, and that would include the type of bonds that are there in the molecule, and we can also look at specific combination of certain atoms within those organic molecules, and that gives us what we call a functional group. And examples of such things, it's, for example, when you have the carbon-to-carbon bond being single bonds, this becomes a functional group for a specific type of hydrocarbons. In this case, all carbon-to-carbon bonds are single bonds, just one bond between carbon atoms. The second one could be a situation where you have a double bond between carbon atoms. If you have got a double bond between carbon atom and it is one double bond between carbon atoms in that molecule, what you have would be specifically some organic molecule that belongs to a particular functional group, and I'm going to explain it further as we move on. So here we have got double bonds between carbon atoms. The last one, we can have a situation where we have triple bond between carbon atoms, and that again lends itself into another functional group that we are, of course, going to talk about. So these are functional groups. It can depend on the bonds, number of bonds between carbon atoms. It can also depend in the type of bonds or the type of atoms involved in the bonding as well, to tell us the functional group of an organic molecule. Continuing with terminology, let's look at these two here now. The homologous series, and then we will be talking about the type of organic molecules that these homologous series are based on. What is a homologous series, or what are homologous series? A group of organic molecules with the same functional group and the same general formula. That forms a homologous series. Okay? For example, alkanes, okay, are a group of organic molecules that form their own homologous series. They form their own homologous series according to this formula here, general formula, CnH2n plus 2. And you may wonder, but what is this N? What is this C? What is this H? Now, obviously, the C, it's carbon, and the H is hydrogen. Okay? And what is N? N is there to represent the number of carbon atoms in the molecule. The number of carbon atoms in the molecule. Okay, so that is what N is for there. Now, I will refer to this again later on when we begin to unpack these type of molecules. The second one, CnH2n, is a homologous series of alkenes. And here we have the general formula as CnH2n. Now I have explained what N is, what the C and the H are. Lastly, we have the alkynes, and in the same way, they do have their homologous series general formula is CnH2n minus 2. Okay? And then in that order, or in that way, again, N is the number of carbon atoms in the molecule, C is carbon atoms, H is for hydrogen atoms. All right. Now, let's move on. Terminology, continued, molecular formula, structural formula. Now, what is a molecular formula? Now, let me explain this quickly. When we have a compound, or if we have, say, carbon dioxide, let me move out of the organic chemistry a little bit. This CO2 here, it's called a chemical formula. And because it's a chemical formula representing one molecule of carbon dioxide, we will call it a molecular formula of carbon dioxide. In other words, it is a formula that tells us about one molecule of that substance. Okay? So a molecular formula here for organic chemistry as well will be a formula that tells us about one molecule. One molecule. Okay? Represented. Okay, so we represent it. Okay? Without showing the bonds. In other words, in this instance, if we go back to our example of CO2, you see it is just CO2. We are not shown how C, O are bonding, whether there is one bond there, or we've got double bonds here, double bond there. We are not shown. All we have at the moment is this one. Okay, so we don't show how the C is bonded to O. It is just telling us for a molecule how many atoms of each component is there. In the case of CO2, we've got one carbon atom, two oxygen atoms together. So it's CO2, and that is the molecular formula of carbon dioxide. But when we talk of structural formulas, here we are showing again it is still one molecule. But the difference is that bonds are shown. In other words, we show which atom is bonded to which one. For example, we can look at methane. We'll come back to it, of course, even later on. Methane is the very first or the simplest organic molecule in the alkanes series, homologous series. It is CH4. That CH4 will be the molecular. Because all it is telling us is that for every molecule of methane, what we have is one carbon atom, one bicarbon atom, and we have got 4 hydrogen atoms. So that is what it is telling us, okay? But then when we come to the structural formula of this methane, then we show how these hydrogens are bonded to the carbon. And that becomes the structural formula. Okay, the structural formula of methane. Right. Now, structural formula then gives us more details in terms of the position of the atoms, where they are found, how they are bonded together. That that becomes important, because nothing stops us from thinking that this C could be bonded to one hydrogen, another hydrogen bonded to another, then one hydrogen bonded to that one, and okay, or things like that. But we know this cannot happen. I'm just giving an example, that the structural formula tells us the exact position where these atoms are within that molecule. All right, let's proceed. Now, in organic chemistry, we do have a naming system. In other words, because carbon has the ability to make chains, long chain molecules, rings of molecules, different ones. How do we name them? How do we differentiate one from the other? Then there is a way, there's a system of naming them, and the name given to it, this system, is IUPAC, International Union of Pure and Applied Chemists, or Chemistry. And that system is used to name these molecules. How is it used? The basic thing about it is, although there is more other things to bring on here, we will bring those things as we proceed, but basically, the systemic naming of these substances is such that for all organic molecules, we have 2 parts to them. We have got the prefix, we also have the suffix. Now, you would know from your lessons from learning English as a language that when you talk of prefix, that will be the first part of a word. Okay? So the first part of the word, and the suffix will be the last part. of a particular term or word. Okay? Now, this last part usually will tell you about the functional group of that particular molecule, where it belongs, okay? Or the groups present in that substance. The prefix, what it will do, it will tell you in terms of the number of carbon atoms present in that long chain or ring of the carbon or the organic molecule, all right, or that particular hydrocarbon. Let's proceed with the IUPAC naming system. All right, let's now begin to look at these prefixes and see how they are used. One, let's start with the very first one. I have already mentioned it. Mirth. Okay? Mirth here would mean that we're talking about the first one, the first organic molecule with one carbon atom in it. Earth would mean the one with 2 carbon atoms in it. Prop for the one with 3 carbon atoms in it. But, the one with 4 carbon atoms in it. And we can proceed, and we come to pent, one with 5 carbon atoms. Hex, one with 6. Hept, one with 7 carbon atoms. Oct, one with 8 carbon atoms. So those are the prefixes that are used. So you read a prefix, it already tells you, oh, I'm expecting a chain of 1 or 2 or 3 or 5 or 7 or 8 carbon atoms here. Okay? We can continue to 9 to 10, but we will stop there because, well, our syllabus allows us to get there and we don't have time to go to the rest of them. But if you have 9, you know that we'll have non. If we have 10, we would have deca. All right? So things like that. In that way, we will be naming them, we'll be using the suffixes to tell us in terms of the number of carbon atoms that are there. With regard to the suffixes, we're saying this is the end part of a term. Okay, the end. We were dealing with the prefixes, the beginning. Now, the end of words, these terminologies. Here, we've got, for example, "-ane" as a suffix. "-ane" as a suffix, with regard to hydrocarbons, it will be referring to, it will be a molecule belonging to what we call alkanes. Okay? And alkanes are these ones where we have got single bonds between carbon atoms. All right? And here, the next one, we can have "-ene" as the suffix. And once we have "-ene" as a suffix, we should know that we're talking about a molecule that belongs to a homologous series of hydrocarbons known as alkenes. And alkenes, these are homologous series, or this is a homologous series for organic molecule that has got at least a double bond between, at least one double bond between carbon atoms. That will be an alkene. Lastly, we can have the "-ine" group, okay? And that would mean alkynes. And alkynes are these hydrocarbons. This is a homologous series where you're having one. We're having at least a triple bond existing between 2 carbon atoms in that molecule. That then tells you you're talking about an alkyne, right? So that is how we make use of the prefixes to name our molecules and our suffixes, all right? So the two together tells us where these molecules are found. Homologous series, are they alkanes, are they alkenes, are they alkynes, okay? And then now we know with alkenes, single bonds between carbon atoms. With alkanes, single bonds between carbon atoms. With alkenes, double bonds between carbon atoms. And with alkynes, triple bonds between carbon atoms. Right. let's move on. Let's look at an example that can help us to learn how to name these molecules or to use what we have just spoken about. The molecular formula of 3 hydrocarbons are given below. Okay, so these are molecular formulas. The question is, for each of them, draw the structural formula of each molecule, write down the IUPAC name, and then identify the homologous series to which each molecule belongs. So let's do this to all the 3. Draw the structural formula. Now we've got 1 carbon atom for number A, so I'm drawing the structural formula. Knowing that carbon can form 4 bonds, there we go. Okay. CH4, 4 hydrogen atoms around 1 carbon atom. And when I have done this, write down the IUPAC name and identify the homologous series where it belongs. IUPAC name, remember we said the suffixes tells us about the number of carbon atoms to it. This is only 1, so it is definitely a meth. But then I need to get the suffix that will tell me to which homologous series does it belong. Now, for me to do that, I need to check the bonds between carbon atoms. Oh, well, for this one, the first one, do I really have to check the number of bonds between carbon atoms? Not really, because I only have 1 carbon atom in this molecule, so there is no way in which it can be bonded to another carbon atom. So that is not going to help in this case. But since I don't have any double bonds, I will think, or I should believe, that I must have an A in there, because that will tell me this has got no double bonds between carbon atoms, and therefore the homologous series to which it belongs will be the what? The alkanes. Okay, beautiful. Okay, so that is how we can get to see this. Now, let's look at the next one. It says C2H4. Oh, C2H4. So if I have C, let me just do this. Before I show the bonds between the C's, I'm guided by CH4. So I might have 2 H's there. And let me just distribute them equally. So I have another 2 there to make it 4. So each carbon atom is capable of making 4 bonds. At this point in time, I only have 2 bonds on each. So that will be bond number 3, and this will be bond number 4. So that you have got 4 bonds around each carbon atom. And immediately it shows me that in between the carbon atoms here, I've got a double bond. Okay? Now, a double bond. Now let me try to name it. I've got 2 carbon atoms, so these must be something to do with earth, because 2 carbon atoms, earth, remember that. Okay, so earth. Now, 2 bonds or double bonds between carbon atoms takes me to a homologous series called alkenes. So this will be ethene, and therefore this belongs to the homologous series called alkenes. Okay, so that is how I could identify that. Let's look at the last one, number C. Okay, we don't have enough space there for number C, so let me just come down here. In fact, I had a whole lot of space here, but let me just use this one for number C. Number C, C3H4. So you've got C3H4. Okay, so I've got C, C, C. I've got 3 of them. Oh, C3H4. So let me check this. If I have 1 carbon bond, one carbon to hydrogen bond here, I can have another one there just thinking aloud here. Allow me to do this. Let me just erase this one quickly. Okay. So I can have, okay, I know there's going to be bonds there. Let me just do it that way. But then I'm only going to have 4 hydrogen atoms around this one. So if I have 1 here, like that, let me just think that maybe let me have 2 here. Okay? So if I have 2 hydrogens at the end and 1 at the beginning, this one can form 4 bonds, this carbon atom. Around every carbon atom, I can have 4 bonds. So if this one is only having 2 bonds, I can have another bond there. So I've got 3 to the first carbon atom. For me to have 4, I can add another one, so I've got a 3. Here, I've got 1, 2, 3, 4, I'm fine. For the last one, I've got 1, 2, 3, so I might need another H. And in this way, I've got 3 H's, 4 H's. Yes, I've got H4. C3, 1, 2, 3, I've got 3 of them. But then, what have I come up with here? Look at it. At that point there, I've got 3 bonds between carbon atoms. And 3 bonds between carbon atoms means that I am in the alkynes homologous series, because that is where I have got 3 bonds between carbon atoms. But then, what is this molecule? The name of it. You have got 1, 2, 3 carbon atoms, so it will be prop. Okay, prop, 3. And the 3 bonds between carbon atoms tells me about what kind of a molecule is it. Does it belong to alkenes, alkynes, or alkanes? So the triple bond says it belongs to alkynes, and therefore that will be a propyne. Okay, so that's how we can use the prefixes, the suffixes to name our molecules, our organic molecules, our hydrocarbons. Okay, let's proceed. Let's look at example 2. Draw the structural formula of the following hydrocarbons. Here, it says here 2-methyl-butane. Now, look at this. Firstly, the main chain here, or the main name here, is butane. And butane is an alkane because but, okay, tells me, it's the suffix, it tells me about the number of carbon atoms. But at the end, the suffix is ane. Ane means it is an alkane. That's what it is telling me. So I don't expect to see any double bonds or triple bonds between carbon atoms. But then there is this first part here. It says 2-methyl, 2-methyl-butane. What is this methyl? And what is this 2? Now, let's go back to the first alkane, methane. It has got 1 carbon atom, and apart from that, it has got 4 hydrogen atoms. Okay? Now, if I were to place these in, I would do it like that. So the 4th hydrogen carbon would come there. Let me use a circle for it. And let me use a different color pen here to explain something quickly. So that is methane with a hydrogen there where I'm pointing. But if I remove that hydrogen and this part here is free, so it is vulnerable to any other substance that would like to bond with it, this thing then becomes what we call methyl. It's a methyl group. Why? Because it has been removed, it has been deprived of its final hydrogen atom that was supposed to be there. Okay, so this becomes a methyl. So that is your methyl. Now, the other question we need to answer is these two here. Okay, these two here. What is the significance of that two there? Okay, these two here tells us the number where this methyl group is attached. Remember I said there is no hydrogen atom there, so it can be attached anywhere. So it tells us the carbon atom number where this methyl group is attached. Now let's start to draw this. We're talking butane, so I have got 4 carbon atoms, butane. And I've got single bonds between them. Single bonds, no double bonds. That's why it's a butane. Now, it says 2 methyl butane. So the methyl group must be on carbon number 2. It doesn't matter where I start counting from. If I start counting from the left, because the counting of the carbon atoms can be done from any side. But if I start from the left here, this will be my second carbon atom. And if I start from the right, this will be my second carbon atom. And if you check here, if you toss this thing around, you would see that the second carbon atom will be second, whether you rotate it and let it start this way or that way. So it doesn't matter where it is. But then for the sake of clarifying this point, because we're going to use it more often as we move on, allow me to number these carbon atoms and say, okay, this is 1. Okay, so this is carbon number 1, number 2, number 3, number 4. So on carbon number 2, I've got a methyl group. That is what the 2-methyl says there. I've got a methyl group. So on 2, I've got this methyl group. I've got this methyl group. Then I proceed. Where do I have my hydrogen atoms? So there is the bond for hydrogen atom. Okay, that didn't come out very nicely. Hydrogen, 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 and here hydrogen, there hydrogen, 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 hydrogen. So I've got my, you see, 2-methyl, so 2 on carbon number 2, 2-methyl, butane. Okay. Now you would also notice here that the main part of the name forms your longest chain. Okay? So it means that in naming these substances, you need to first identify the longest chain and know exactly where it belongs. And then secondly, we have the groups there, which form part of the beginning of the naming of the substance. So we will talk more about it. Let's move on to the next one, and you will see more of what I am talking about. Now this one has got more to it. It says 3-ethyl. Oh, 3-ethyl, 2-methyl, pent-2-ene. Okay, it's a long one. Now, look at it. From here to there, we are getting the longest chain. We are getting what is the root of our molecule here. 5 carbon atoms, pent. Okay, so 5 carbon atoms. Let me write them down here. It's 1, 2, 3, 4, 5. Okay, now it says to me that on carbon number 2, I've got a double bond, and that must take precedence, because the double bond is one very important aspect. You look at it, you first check, do I have double bonds, triple bonds, and that is where you will start counting your carbon atoms. Now, where would I have, it says pent 2 in, so it will be on carbon number 2. If I start counting from the right, 1, 2, so the double bond would be there. Okay? So I've satisfied the pent 2 in there. Then it says 2 methyl. So on carbon number, remember, this is now carbon number 1, carbon number 2, number 3, number 4, number 5. And I've started counting from there because I put my double bond this side. So I must start counting my carbon atoms closest to my double bond. So I had to start from that side. So when it says 2 methyl, it means the methyl group is attached to a hydrogen, to a carbon atom number 2. So it will be here. So here I'll have a methyl group. So let me write it down. Methyl, remember the methyl? Okay, that is the methyl group. So it is on 2. Now I continue. It says, on carbon number 3, I've got an ethyl group. So carbon number 3 here, I've got an ethyl group. Ethyl group, 2 carbon atoms. So I would have that, if you like. So, and those will be bonded to hydrogen. Okay, pardon me for the space, but I think you can see what I am doing there. That is your ethyl. So let me just highlight them nicely for you. This one is your methyl on carbon number 2. Okay, and this one is your ethyl group on carbon number 3. Okay, so it means that the rest then would have their normal hydrogen atoms around them. H, 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 H there. But make sure that this is crucial. Make sure that the bonds around the carbon atom are 4, not more than 4 and not less than 4. They are always 4. So let's look at it. You see here 1, 2, 3, 4. That is around carbon number 5. Around carbon number 4, 1, 2, 3, 4. Around carbon number 3, 1, 2, 3, 4. Around carbon number 2, 1, 2, 3, 4. Around carbon number last, okay, and number 1, there we go. We have CH3 there. We have got that one. There's 1, 2, 3, 4. So that has to be drawn like that. Okay. Now, so we are drawing structural formula of these things, and I think you are following it so that you are sure of what to do when you are to draw this structural formula. You carefully place things exactly where they are supposed to be, but you check that name carefully and do it. Okay. Now let's look at this one. It says 3.4 dimethyl pent 1 in. Oh, okay. Now let's look at the last part. Pent tells us 5 carbon atoms. Okay, 5 carbon atoms. Now, ine tells me there's going to be a triple bond, and closest to the triple bond, that is where I'm going to begin to count my carbon atoms. But the root structure here is that of pent. So I've got 5 carbon atoms. 1, 2, 3, 4, 5. Now if I start counting from the left, it says pent 1 in. So on carbon number 1, I can start from the right. It doesn't matter, it will be all the same. But for now, because for the past ones I've been starting from the right, allow me to start from the left. So here, Let's number these carbon atoms again. So this is number 1, number 2, number 3, number 4, number 5. I did 5 because my name says pent. Okay, so 5. Right. And it says pent 1 ion. Now 1 means on carbon number 1, that is where I've got the ion series, and that is the triple bond. That tells me that this thing belongs to a homologous series called the alkynes. So that is the homologous series where it belongs. Okay? So I have my triple bond. If I have the triple bond there, it means the last bond is just 1, and it's going to be to the hydrogen. Okay, so it's 1 ion, 3.4 dimethyl pentane. So this means on carbon number 3, this 3.4 means on carbon number 3, I've got a methyl group. On carbon number 4, I also have a methyl group. Why both of them? Because it says dimethyl. Di means 2. Okay? And it says on 3 and 4, 3.4 dimethyl. So on 3, I've got a methyl group. And then on 4, I also have a methyl group. Okay? Now, I could have had my methyl group on number 4 here at the bottom, somewhere here for carbon number C. But I don't want to write it there because, you know, I have to show the structural formula. I'm going to write things that are going to overlap with my first methyl group, and it's going to make everything look very ugly. I don't want that to happen in my writing, especially when I'm doing my exams, because the examiner or the markers there also want to see clearly what I have written. Okay, so now, where are the hydrogen atoms? You see here, we had already shown it because we said if 3 are there, the 4th one will be for hydrogen. But here, let's check on carbon number 2. Do we have 4 bonds? We have 1, 2, 3, 4. Okay, so that is fine. Carbon number 3, do we have 4 bonds? 1, 2, 3. We don't have the 4 bonds. So it means here we need to show our hydrogen there. Okay? Carbon number 4, do we have 4 bonds? 1, 2, 3. No, it means we have another hydrogen that should come in there. The last one, how many bonds? 1. So we need to show the rest. The 3 other bonds are bonded to hydrogen atoms like that. And this is my 3.4 dimethyl pent 1 ion. And that is the name of this molecule here. Okay? Now let's come to another one. This one is called cyclobutane. Oh, cyclo. The word cyclo means I've got a cycle here. In other words, I've got a ring molecule of butane. Now, butane, that tells me is an alkane. So single bonds between carbon atoms. Single bonds of C to C, single bonds. But then but tells me that I must have 4 carbon atoms. Okay, so how am I going to do this one? I would then have, okay, I would have C to C to C to C. I must have another C here. I'll have C to C to C to C, and that will be a bond there. So I've got single bonds between carbon atoms. Okay, don't want this. So that is what I have. It's a ring, cyclo, a ring. Okay, Now, how am I going to have the hydrogen atoms here? Obviously, I've got a situation where if I add 2 hydrogen atoms there, 4 bonds are taken. Okay, another one there for this one. Allow me to do it this way. Let me remove even this one. Let me try to. So if you have got your one hydrogen here for this one, you have another hydrogen there, hydrogen here, a hydrogen there, hydrogen there, hydrogen there, and then the same way, hydrogen there, hydrogen there. So you would see that onto each carbon atom, all that is attached to it is 2 hydrogen atoms, because the other 2 bonds are used to bond to another carbon atom. So you've got a chain, you've got a ring. This is a ring molecule. Okay, so because it's a ring, the starting part, cyclo, okay, cyclobutane. Now it is different from butane as butane, I mean linear butane. Why? Let's look at it. If I've got linear butane, what I will have is this. Okay? What I will have is this. That is the structure that I will have. That will be linear butane, or a chain type of butane molecule. And if you check here, you would see that you've got 1, 2, 3, 4 carbon atoms. Here you've got 3 hydrogen atoms, 3, there's 6. Then you've got 8, you've got 10. So it would be C4H10. But for this one, it won't be C4H10. Why? Let's look at it. You've got 2 hydrogen atoms for every carbon atom. So what you will have here for this one, it's this molecular formula. It's going to be C4H8. Okay? Now, this is cyclobutane. That is butane linear structure. And they are, both of them are butanes, but they are not the same in terms of chemical properties. They are not the same, because one has got 10 hydrogen atoms on it, the other has got 8 hydrogen atoms on it. One is a cyclobutane, so and the other one is linear. The two will behave very differently chemically when we look at them. All right, so that's how we could draw the cyclobutane. Let's come to the last one. Okay, here. In fact, yes, the last one, 2.5. Cyclobutene. Okay, now cyclobutene, let's look at it. It's again a ring formed of 4 carbon atoms. But it says butene, so I'm expecting a double bond somewhere. Okay, so let me place my double bond there. Okay, and then if I place my double bond there, my hydrogens, my hydrogen atoms, for this C here, this carbon here, I'll have 1, 2, 3, so I only need 1 more bond. So that will be the bond to hydrogen. This one on top here, again, for it, I will also be having 1, 2, 3 bonds that has been used already. The only one remaining is a single bond to a hydrogen atom. Okay, in that way. Then for this one, oh, I still have space for this one, so I can have hydrogen there, and then perhaps another hydrogen up there. Okay, so I can have another hydrogen here for this carbon. And the same thing here, I can have hydrogen there and another hydrogen there. Okay, so that's how it would have happened. Why? Because we're looking at making sure that each carbon atom has 4 bonds around itself. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 for each of the carbon atoms. And that is how we can move from given names and coming up with structural formulas. And you can see that the naming of organic molecules, it's actually so much tied to the structure. You need to explain and show the structure, because it is in the structure of the organic molecule where we begin to see different behavior of molecules, although some of them might be having the same number of carbon atoms and same number of hydrogen atoms, but the way these atoms are arranged around each other, the way they have bonded against each other, it is different, and therefore that also dictate the kind of chemical properties that these molecules are going to have. All right, now let's move on. We're now going to have to look at another example. We're going to look at example 3. Let's see how we can use our knowledge now of naming molecules to name the ones that we have here. Okay. The question is, give the IUPAC name of the following. Okay. The IUPAC names of the following organic molecules. Let's look at it. The first one, 3.1. I said the first thing you need to do is to identify your longest chain. Now look at this. This is your longest chain. And when we talk longest chain, we're talking about the chain of carbon atoms. So there is your longest chain. How many atoms of carbon are we having in this longest chain? We have got 4, okay? 4 atoms of hydrogen, and therefore I'm thinking it will have something to do with butane. So I'll write but, okay? That is the prefix. Do I have any double bonds between carbon atoms or triple bonds? The answer is no. So I only have single bonds between them. So it will be an alkane. So the last part will be ane. So this is butane. There is nothing very very different or very special about this molecule now. It is just butane, 4 carbon atoms in the longest chain, no branch of any other carbon atoms here. We just have 4 carbon atoms stretched along that chain, and therefore that is butane, no double bonds between them. Okay, now let's move on to 3.2. 3.2, wow, now there's something here. Here is a molecule. It has got what we call a branch on it, a branch of carbon, atom bonded to hydrogen atoms. Now, I need to name it. I need to identify my longest chain. Now, longest chain, this could be a longest chain. Okay? So my longest chain consists of 3 carbon atoms, and I'm therefore expecting a name that will say something like this. It will have something prop in it. Okay? Do I have any double bonds between carbon atoms? No. Triple, no. All are single bonds. So it is going to be a propane because single bonds. It's an alkane. Fine. But what is attached to it? What is this other piece here that is attached to it? Oh, yes. What is attached to this molecule? It's a carbon atom attached or bonded to 3 hydrogen atoms. And therefore, this is a methyl group. So methyl group would mean that this is methyl propane. So I would then write it as methyl propane. Now, do I have to number the carbon atoms so that I can specify where my methyl group is? Well, in this case, it's not necessary. But then you can see that the reason why we say it's not necessary here, if I number my carbon atoms from left, this will be carbon atom number 1, number 2, number 3. If I decide to number them from the right, this will be carbon number 1, number 2, number 3. So what does it mean at the end? It means that it doesn't matter from which side I count or I number my carbon atoms. The carbon atom to which the methyl group is attached is always carbon number 2. Okay, so this will be 2-methylpropane. So whether you say 2-methylpropane or just methylpropane, you mean one and the same thing. 2-methylpropane won't be different from methylpropane. Okay, so in other words, we cannot have 1-methylpropane. It's not possible. Right, let's move on to example 4. And example 4 is going to introduce to us something called isomerism in organic chemistry. So we'll be talking about isomers. And listen carefully because I'm going to define that term now. Right, so here the question is, or what we're required to do is to draw and name 5 isomers of C5H10. What is an isomer? Perhaps that is where to start. Let's start by defining that. An isomer, or what are isomers? Isomers are organic molecules. They are organic molecules with the same molecular formula, okay? Formulae, let me write it like that. But different structural formulas. Structural formulae. Okay, so that is what an isomer would be. Now we are here going to be writing or drawing structural formulas of C5H10. They will be different from each other, but they will be the molecular formulas will be the same. So let's start. Let's have the first one. Let's call it A. I would have my 5 carbon atoms. Okay, 1, 2, 3, 4, 5. Okay, and because it's H10, remember if it was an alkane, I would be having more than 10 hydrogen. I will be actually having, it will be C5H12, but it's not H12. It is C5H10. It's not this one. So the fact that it is C5H10, it means that somewhere I've got a double bond. That double bond could be anywhere between carbon atoms. So I can have it there, okay? Or I can have it, let's have B. We will come back and put the H's there. Or I can have it here, all right? Now, why can't I say I can also have it there and have C? It's because, I mean, this is symmetrical. If this molecule here can be turned around, this bond will be here. So this one and whatever you get when you turn it around is the same. It's going to be the same. So even with the first one, number A, if I decide to take this double bond and put it here, I'm still talking about one and the same molecule. So that is not a problem at all. So we understand that. Now the question is, where will the other 5 come from? Okay, the other 3 to make it 5 come from. Now here is where they come from. We can have a branch to this. We can have, okay, so there we have, let me do it this way. We can have a long chain of 4 and have a branch like that, Okay, and when we have a branch like that, we can then again in the same way say this could be there, okay, the double bond could be there, or the double bond could be here, so we can have even more, all right? And then now, the fourth one, we could have C, 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 and we can have another branch if you like. I mean, we can have the branch, the same one, but then move this double bond, and instead of it being closer to the methyl group, we put it there. So we have another structure there. Then E, the fifth one, we can have also a situation where we have a ring structure of pentane, for example. Okay, so here we have got 5 carbon atoms bonded together in a ring structure, and that will be an isomer of the rest. Now let's put in the hydrogen atoms now. Okay, let's go back up there quickly. Right, let's now go back and put in our hydrogen atoms now around our structural formulas. Now, on number A, okay, we've got 1 bond there, so I can have, it's 1, it will be 2, 3, 4. So there are my hydrogen atoms. Okay, here, there, and there. I would have it here and there. And here I must be careful, 1, 2, 3, so I will only have 1 there. And then here it's 1, 2, I can have 2 here, 2 more to make it 4 bonds around carbon atoms. If I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is C5H10. All right. The next one, B, 1 bond there, I can have 1, 2, 3 more, so 3 hydrogen atoms around this one. Here, 1, 2, I must have 2 here to have 4 bonds around the carbon atom. 1, 2, 3, I must be careful, I will only put in 1 there. Here again, 1, 2, 3, I must be careful, I can only put 1 there. Let me put it up there. And then 1, oh, here I've got 3 more to put. Okay, so H, H, H. You can count again, 1, 2, 3, 4, 5, 6, 7, 8. I need to count carefully here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's again C5H10. But the molecular structural formulas are not the same, the structures are not the same, the molecular formulas are the same. And these are called isomers, okay? Coming to number C, I can have 1, 2, 3 here. And I can have 1, 2 here. I can have 1, 2, 3, 1, 2, 3, 4. I can't have anything here. I think you can see there. Nothing around this one. But then here, on this branch, I would have the 3. And then here I've got 1, 2, so I can only have 2 more there. Okay, 2 more bonds. We'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's again C5H10. So it's an isomer of this molecule as well. The last one, let's look at, not necessarily the last one, number 4. Here, 2 more. All right. And then 1, 2, 3, I can have 1 here. 1, 2, 3, another one here. Then 1, 2, 3 here. So that I have 4 bonds around the carbon atom. Okay. And then there I would have again 3. Okay. H, H, H. You can count, it will come down to C5H10. Right, let's come to this one. This is a cyclic molecule, right? So here, 1, 2 bonds, I'll need another one there, I need another one there, so 4. 1, 2 bonds, 4. 1, 2, 4. 1, 2, 3, 4. Okay, this is an H, and then 1, 2, 3, 4. Okay, so you will see this is again C5, H10, but this is a ring structure of the molecule. So all these 5 here, these are 5 isomers. These are all isomers. Why do we call them isomers? Remember, they've got the same molecular formula. So C5H10, 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 C5H10. But what is different about them? The structural formulas are not the same. That structure is not the same as this structure, it's not the same as that structure, and it is definitely not the same as that structure. So that is the essence of isomers. That's what you need to know about isomers. Okay, now let's move on to talk about the physical properties of organic molecule, the hydrocarbons. We can talk here about their melting points. At what point do they melt? We can talk about their boiling points. At what points do they boil? We can also talk about their viscosity. Now, this is one nice term. What is viscosity? The ability of a liquid substance to flow, okay? Ability of a liquid substance to flow. A liquid substance to flow. Now, this is tied up to the issue of intermolecular forces as well, because the stronger the molecular forces, we can then say perhaps the viscousness of that particular substance will be low. In other words, it will be difficult for it to flow. So viscosity has to do with how easily a substance is able to flow. Okay, a liquid substance for that matter. Okay, now let's look at example 5. And under example 5, we're looking at melting points and boiling points. MPs and BPs, okay? Melting points, boiling points. Now, if you look at this table here, and we're specifically looking at alkanes, methane melts at minus 183 degrees Celsius, and it boils at minus 164 degrees Celsius. Now, what does it mean if it boils at minus 164 degrees Celsius? It means at room temperature, it is a gas. Gas at room temperature. Because room temperature is about 25 degrees, so this thing has already boiled at that point. The same thing here. So this would be gases at room temperature. But let's look at octane. Octane boils at 125 degrees Celsius. Okay? So it means at room temperature we can have this one still in a liquid form. Okay? Now you would understand octane. Here, this is when we begin to talk about petrol. Okay? Now, let's move on. Eicosane, this one, look at the boiling point. 343 degrees Celsius. We can expect this one to be a solid. Now, I also want you to check on something. This is a solid. Look at the number of carbon atoms, okay, in that chain of the eicosane molecule. That tells you this is going to be a solid. Here we've got 8 carbon atoms. It is a liquid, okay? Butane, we have got 4. It's a gas. And up here, all these are gases, okay? And then they've got lesser number of carbon atoms. So the lesser number of carbon atoms, the more you are having those molecules as gases. Somewhere in between, okay, 8, 9, 10 to 12, 14, somewhere there, you have this organic molecules as liquids. But when you go way up, where you've got chains, molecules of long chains like 20 carbon atoms, 25, you begin to have solids, okay, at room temperature. Right, now let's look at the questions quickly. Identify a hydrocarbon that is a liquid at 25 degrees Celsius. Now, I told you 25 degrees Celsius is room temperature. The only one that is a liquid at room temperature here is octane. I have explained it. There it is. So octane will be a liquid. Why not the others? These ones would have boiled and become gases long time before you reach 25 degrees Celsius. Coming down, so this one will be octane. Coming down here, describe what happens to the melting points and boiling points when the molecular mass increases. Now, molecular mass is increasing with the number of carbon atoms. So it is increasing as you go down this table here. That's the molecular mass. What is happening with the boiling points and the melting points? Look at it. Boiling point increases. Okay, this must be the melting point. The melting point increases. Okay, increases as the molecular mass of the substance increases as well. What is happening with the boiling point? We can check the same thing is happening. Look, from minus 164 we come to minus 89, minus 0.5. We suddenly at 125. We are way up at 343. So the boiling point is also increasing with molecular mass. Okay? So, okay, we would then say that both the boiling point, both the boiling points and melting points of the organic molecules increase with the increase in molecular mass. So when the molecular mass of an organic molecule increases, the boiling point and the melting points of those molecules increases as well. Okay? Explain the trend you have identified. That's exactly what we are seeing. Explaining why it is happening like that. As the molecular mass increases, what we also see happening as the molecular mass increases, okay, the intermolecular force intermolecular forces becomes bigger. Okay, so when they become bigger, they hold these molecules more tightly together. Then we move from gases where the intermolecular forces are small, so molecules are far apart from each other. We come to liquids where now the forces are bringing them more closer to each other. Intermolecular forces increases with the molecular mass, and then when you come to solids, they are closely tied to each other with these molecular forces because they are now even more stronger, and therefore with that, that is the reason why we're seeing this trend here. We're explaining why the trend of boiling points and melting points are actually increasing with increase in molecular mass. All right. Now, that brings us to the end of today's lesson. I hope you enjoyed it, and I wish you well in your preparation for the exams. As always, my name is Tinyiko Kosa. Ciao.